Welcome to this explainer. Okay, today we're going to completely transform how you think about gravity. We interact with it every single moment of our lives, from just dropping a rock on the ground to watching astronauts float on the International Space Station. But by the end of our time together, you're going to see that moving from the simplest falling object all the way out to the extremes of the cosmos reveals some of the most profound secrets of our universe. Here's our roadmap for today's journey. We'll be covering unlearning how things fall, the math of free fall, the myth of zero gravity, Einstein and extreme gravity, and finally, applications and future frontiers. Let's dive in. Section 1. Unlearning how things fall. It's honestly kind of staggering when you think about it. For literally 2,000 years, humanity's understanding of gravity was dominated by Aristotle, who just assumed heavier objects fell faster. Makes intuitive sense, right? Well, it wasn't until Galileo in the early 1600s that someone actually did the experiments to prove that all objects accelerate uniformly, regardless of their mass. Then Newton linked this to the cosmos, and Einstein later redefined the whole thing entirely. It took massive chronological leaps just to correct our initial common sense guesses.
And you know, this perfectly illustrates the core of our confusion. Down here on Earth, our intuition is totally blinded by air resistance. A feather drifts, a hammer drops. But jump forward to the Apollo 15 lunar mission in 1971. Commander David Scott actually performed this exact test in the vacuum of the moon. And without air resistance getting in the way, the hammer and the feather fell side by side and hit the lunar surface at the exact same moment. It was a beautiful confirmation of Galileo's centuries-old prediction. So we really need to define what free fall actually means in physics. True free fall requires that gravity is the absolute only force acting on the object. That means a skydiver just jumping out of a plane, they aren't technically in pure free fall. The air resistance pushing up against their body completely disqualifies it. True idealized free fall really only happens in a perfect vacuum.
Moving right along, Section 2, the math of free fall. Now, take a look at the square relationship of acceleration we have here. It's fascinating. If an object falls for 2 seconds, it doesn't just fall twice as far as it did in 1 second, it actually falls 4 times as far. 3 seconds, 9 times the distance. 4 seconds, 16 times. This proportional growth explains exactly why a dropped object seems to just rapidly zip away from you the longer it's in the air. But here's a wild detail. That standard acceleration rate, you know, the famous 9.8 meters per second squared here on Earth, it isn't perfectly uniform. It actually fluctuates. Because the Earth bulges at the equator, gravity is actually slightly stronger at the poles. It also gets weaker at higher altitudes, and get this, it even changes based on the density of the rocks and mineral deposits right beneath your feet. Geologists literally map these tiny gravitational anomalies to study what's hiding in the Earth's crust. So the really crucial point here is how all this applies to projectile motion. Because in physics, horizontal and vertical motion are completely independent of each other. If you take a ball and drop it straight down, and at the exact same time shoot another ball completely horizontally from the exact same height, they will hit the ground at the exact same time. Gravity pulls on them vertically in the exact same way, totally ignoring how fast that second ball is flying sideways. It's a complete plot twist for our everyday intuition.
All right, Section 3, the myth of zero gravity.
So it is a huge, widespread misconception that going into space equals zero gravity. The International Space Station, for example, is only 250 miles above us. And at that altitude, Earth's gravity is still pulling with 90% of the strength it has right down here on the surface. So if gravity is still grabbing onto them with that incredible force, why in the world do the astronauts float? Well, the answer is orbital motion. The astronauts aren't experiencing zero gravity. They are simply falling. But the space station is moving horizontally so incredibly fast, we're talking about 17,500 miles per hour, that as it falls downward, the spherical Earth literally curves away beneath it at the exact same rate. They are in a continuous, perpetual, elegant state of free fall. And that is what creates the illusion of weightlessness.
Which brings us to Section 4, Einstein and extreme gravity. Back around 1907, Albert Einstein had an epiphany that he later called the happiest thought of his life. He realized that a person in free fall wouldn't feel their own weight at all. This profoundly simple, deeply human realization was the spark. It was the exact idea that would eventually ignite the most revolutionary physics theory of the 20th century.
And this led directly to the equivalence principle. Picture this. Imagine you're in a closed, windowless room. If that room is accelerating upward through empty space at 9.8 meters per second squared, it would feel exactly the same as sitting in a stationary room right here on Earth. You literally couldn't tell the difference. Einstein realized that gravity isn't really a pulling force at all. It is the curvature of space-time itself. Free fall is simply an object following that natural curved path. Now, check out how this space-time curvature, or gravitational acceleration, shifts across different planets. The moon is tiny, pulling at just 1.62 meters per second squared. But look at Jupiter. Even though Jupiter's mass is astronomically huge, its surface gravity is surprisingly only about 2.5 times that of Earth. Why? Well, because Jupiter's massive radius places its surface so far away from its center, and that extra distance partially offsets its enormous mass. Pretty wild, right? But when we move out to the absolute cosmic extremes, our standard equations really start to break down. On a neutron star, gravity is 100 billion times stronger than on Earth. Falling toward one would result in violent spaghettification, literally stretching you out like a noodle. And black holes. They curve space-time so intensely that not even light can escape. Yet, surprisingly, an object in pure freefall wouldn't even feel a sudden jolt as it crossed that point of no return.
Finally, let's wrap up with Section 5, Applications and Future Frontiers.
Let's take skydiving for a second. 120 miles per hour is the standard terminal velocity for a belly-to-earth skydiver. That is the exact speed where air resistance pushing up perfectly balances gravity pulling down. But contrast that with Felix Baumgartner, who famously jumped from 24 miles up in the stratosphere. The air up there was so incredibly thin that there was barely any resistance at all, allowing him to actually break the sound barrier while in freefall. And think about the GPS in your phone. Because GPS satellites are further from Earth's center and moving so fast in orbital freefall, Einstein's relativistic effects mean their onboard clocks actually tick faster than ours do on Earth, by about 38 microseconds a day. That sounds tiny, but if engineers didn't program the satellites to artificially correct for this, our global navigation systems would fail completely within a single day. All of this just goes to show how the incredibly simple act of dropping an object has evolved into our absolute most sophisticated technology. Today, we've got satellites proving Einstein's theories to mind-boggling precision. We're using lasers to measure gravity by dropping ultra-cold atoms. We've got experiments at CERN proving that antimatter falls down exactly like regular matter. And of course, giant facilities like LIGO are out there detecting the actual ripples in space-time caused by colliding black holes. It is genuinely amazing to think about. If the exact same physics rules the mundane drop of an apple in your garden and the unimaginably violent collision of black holes millions of light years away, what other fundamental cosmic truths are hiding right in front of us in our daily lives? Thank you so much for joining me for this explainer. Keep asking questions, and I really hope you never look at a falling object the exact same way again.